Yeah, so I'm going to talk about the first ice-free day in the Arctic Ocean and how that might occur before 2030, and that's based on work that I did with Celine, who was here earlier in the program, not during the conference, but during the Institute, and that was published late last year in Nature Communication. So I wanted to start with kind of looking at the current projections for the first ice-free Arctic. And those are all based on ice-free conditions in the September monthly mean. That second part is something that we sometimes forget to say. We just say first ice-free conditions. But we're really talking about the September monthly mean. Ice-free also doesn't actually mean no ice. It means kind of practically ice-free. So the threshold that's been used is 1 million square kilometer of sea ice, which might look like that, could be a little bit more spread out if the concentration isn't as high. But mainly it means that most of the Arctic Ocean basin that used to be covered by sea ice, even at the end of the melt season in September, will be open, and you can send ships through the Arctic that don't even have to be ice strengthened anymore during that part of the year. And so based on the CMIP6 models for different forcing scenarios, from the weaker forcing to the strongest forcing scenarios, we can see that the kind of likely threshold, 66% using the IPCC language, is crossed sometime in the 2040s for all the different scenarios. And so first ice-free conditions in the September monthly mean are likely to occur before mid-century. And so that's something that we've known for a while, since 2020. We also see that there's no scenario impact because that happens in the relatively near future, where the difference between the different scenarios isn't that big yet, and so the impact on Arctic sea ice isn't that big, because the first occurrence of an ice-free Arctic is going to be primarily determined by internal variability, which overcomes these differences in the force response, because the variability in sea ice can be really, really big. But the first ice-free day will occur before the first ice-free monthly mean, but it could actually occur a lot earlier than the first monthly mean. And so this is just looking at one possible simulation where the dark blue is the daily minimum and the lighter blue is the monthly minimum. And so here we can see that we actually have 4 instances of ice-free days occurring before, on the 5th occurrence, we have the first monthly mean ice-free conditions. So the difference in this particular case from one of the CMIP6 models is that the offset is 21 years. So that's quite a lot earlier seeing a first ice-free day compared to the first ice-free months. And so we asked the question, how soon could the first ice-free day occur? In particular, how much earlier than the first ice-free months, which is what we've been focusing predictions on so far. And so the question is, why do we care? There's nothing magical that happens once the threshold is crossed. It's really just become kind of one of these thresholds, like when we've passed 400 parts per million CO2 in the atmosphere, kind of that was the threshold we passed. An ice-free Arctic, it is kind of a symbolic transition. Like, we as humans will have changed a landscape fundamentally from a really white, ice-covered Arctic Ocean, even in the summer, to a blue Arctic Ocean. So people talk also about the transition from a white to a blue Arctic. Note, we only talk about it in the summer. It doesn't mean the sea ice doesn't come back. It comes back for a really long time afterwards. The other reason we really wanted to look at the first ice-free day is, like last year, we crossed the first we had the first couple of months where the monthly temperatures were 1.5 degrees above pre-industrial, and so there was a lot of discussions in the media, have we already failed the Paris Protocol target of staying below 1.5 degrees? And that really made it clear to me that, like, we're not very clear often when we talk about this. We say 1.5 degrees. We don't say, oh, we mean it in the climatology mean. Of course, that's in the IPCC report, but you have to read the whole thing to really get that. Similarly, with first ice-free conditions, we just say that. We don't necessarily say monthly mean. People probably wouldn't assume we talk about something abstract like the monthly mean, but when it actually happens. And that's where we're going to see the first picture of an ice-free, of a blue Arctic, is going to be in the daily satellite pictures. So we wanted to kind of be able to set realistic expectations of what we could see happen in the future. So to do that, we looked at all the CMIP6 models that had daily sea ice concentration output. And instead of just looking at the raw data, we looked at it compared to how long it would take from kind of the present day sea ice, because as we heard yesterday, François was talking about how we've kind of been in this plateau where we haven't really lost much sea ice area over the last decade or 12 years. And so really the question we wanted to ask is like, once we kind of leave this plateau, once we start going below kind of this area, the 4 million square kilometers in the monthly mean that we've kind of been bouncing around, how quickly could we reach a first ice-free day? So we went from the first ice-free day backwards to the last time that the sea ice area was above or equal to the 2023 daily sea ice area minimum, which was 3.3 million square kilometer. So that was the most recent minimum, but it's very similar to what we've had in recent years. Then we looked how many years evolved between that. That also helps a bit with the mean state biases that we've heard about in Arctic sea ice projections, because it kind of shifts it a little bit, kind of gives each model the same starting point. When is the last time that they had sea ice area similar to what we have today? So this is what we found. So overall, we looked at over 600 model simulations. These are just looking at kind of selected model simulations that do decently over the historical period. So that meant we retained 11 models, overall 366 simulations. And here, because we know that there's a lot of internal variability, in Arctic sea ice, we look at the earliest ice-free day from these models, so the earliest ensemble member and the latest, to kind of get an idea of the range. And so what we find is that the first ice-free day could actually occur within 3 years. One model simulation had that, and several more show that within less or equal to 6 years. But it could also take 50 years or more, or if we look at the, even for the earliest, or if we look at the latest ice-free day, so that's just determined by internal variability, whether we get an early, a late, or something in the middle. Again, kind of, it could take 50 years, or it could not reach ice-free conditions at all. In particular here, we have some that don't reach ice-free conditions at all, even in the earliest ensemble member. And so that's consistent with what's been shown for monthly ice-free conditions, that if we stay globally warming below 2 degrees in the long-term mean, there's a small chance of not seeing any ice-free conditions if the internal variability kind of cooperates. The other thing we notice is that there is no strong scenario dependence, so especially for the earliest occurrences of the first ice-free day, because again, it's driven by internal variability. We actually, the very fastest ones are kind of the middle scenario, so from SSP 126 to SSP 370. We do have a scenario dependence for the late ones, so the lower the scenario, the later that happens. So how much earlier than the monthly mean is that? So on average, the 21 years that I showed earlier is kind of on the long end. Most of them for the earliest ice-free day occur within 6 years, sometimes the same year, sometimes a couple years delayed. But we do have some ensemble members where they're delayed, especially if we have an early ice-free day compared to the ensemble spread. For the latest ice-free day, most of them occur in the same year or within a year or two, because that means you're already like behind the ensemble mean. So in the forced response, it's the internal variability would be delaying the first occurrence of a first ice-free day, and so then usually happens in the same months. Yeah, this was looking at the months, the same analysis just for the monthly mean, and that's really generally in agreement with other CMIP6 analyses, where the highest probability kind of is between 11 and 30 years, which puts us at the late 1930s to the late 2050s. So again, in agreement with the prior analysis. But also we have two simulations here which have it in 6 years or less, and they're actually two of the same ones that also have the first ice-free day that fast. We were actually surprised that we had some that went ice-free within 3 years. That wasn't what we expected. And so we decided to kind of take a storyline approach and look more in detail at these simulations. And so overall, there were 9 simulations that out of the 366 across 4 different models that reached ice-free conditions within 6 years or less. And so the storyline approach is kind of a different way of looking at climate simulations. So it's a way to look at a physically self-consistent, unfolding of plausible past or future events. No a priori probability of the storyline is assessed. Emphasis is placed instead on understanding the driving factors involved and the plausibility of those factors. And so we're not saying these are most likely. Obviously, they're not. We're just saying what could actually do this? What could get us to an early ice-free Arctic that quickly? So how do these quick transition simulations do that? So I'm just going to show you 1 out of 9 for simplicity, but in the paper we show all 9. And so all of them have a very rapid drop over several years in the daily minimum, and kind of a steady drop. So it's not just 1 year that kind of gets us there. It's kind of a steady drop over 3 to 6 years. The other thing that happens in all of them is that after the first ice-free day, there is a bounce back afterwards before the next ice-free day happens, at least with a difference of 1 year compared to, so it doesn't stay ice-free or go ice-free year after that's first reached. Then we look more, what are the kind of the conditions that lead to this extreme sea ice loss? And the first thing we noticed was when we applied the criteria for rapid ice loss events, which Francois also nicely introduced yesterday already, we found that actually all of these 9 simulations, this quick transition to the first ice-free day happens during rapid ice loss events during August and September for all of these quick transition simulations. And so that leads to this large drop in the sea ice area, particularly in the summer and into the fall, but not so much in the winter time. However, we do actually see, if we look at the sea ice mass, which is here monthly mean, because daily sea ice volume or sea ice mass was not available. So again, daily output's really, really useful here. But so we had to go back to the monthly output. But what we see here is that we see a big reduction, at least leading up to the first ice-free day, also during the winter time. So it's not just the summertime thinning of the area, but overall reduction in the sea ice volume. So year-round, so the ice doesn't expand as much anymore in volume, or doesn't grow in volume as much during the winter time, leading up to this first ice-free day. So what causes that? So what we found was that it seemed to be primarily driven by the atmosphere. We have very warm fall, winter, and early spring temperatures. So the black shows the pre-2023 mean temperatures, the dark blue the last year at 2023's conditions, and then the pink is the first ice-free year, kind of going there. And so we can see that we have much warmer temperatures during the fall as the ice-free season gets later and later, but also during the winter time with several instances of daily average surface air temperature being above minus 20 Celsius, which is kind of the threshold for wintertime conditions in the Arctic. And what causes that, it seemed that there was a lot of high pressure pressure systems, and we looked at that in some more details. We have the plots in the paper too, where there is a lot of blocking events that seem to happen during the winter time that kind of enable these really warm temperatures, which prevents a lot of sea ice formation, and then if it lasts into the spring, also helps with melting the sea ice. Also, there's some strong storms. So again, this is just one example. They're all a little bit different. So like we talked about yesterday, 2007, 2012, they weren't caused by the exact same mechanism. The same thing here. They were all really warm. They all have a lot of blocking events. But the exact sequence that leads to the first ice-free day is different for each of them. Some have a lot of storms, especially in the final year or final 2 years, that break up the ice and enable more lateral melt. Some have a lot of blocking, really long-lived blocking events and warm air intrusions that make it really, really warm. But they all definitely have a lot of more blocking events. And we know from other model studies that that's something that we're expecting to see in the Arctic as the climate warms, and something that we actually already are starting to see. So this winter was incredibly warm in the Arctic, broke several records on the monthly means, with really, really warm temperatures. So finally, is it likely that we'll actually see a first ice-free day by 2030? No, it's actually very unlikely. So again, these were 9 simulations out of those 366. So the probability might be the percentage might be different if we had more simulations, but if we do calculate it, it's 2.5%. So obviously it's a rare event, but it does happen in more than just one simulation. And the Ryle events that we found kind of lead to these first ice-free days, they do occur in all CMIP6 models, again, as François mentioned yesterday, in this paper that Annelies Sticker wrote, which is now in press in the cryosphere. And in fact, she has these two plots in her paper, which show the sea ice volume at the start of Ryles in CMIP6 models for low and high emission scenarios, and the sea ice extent at the start of Ryle events. And we're actually kind of right in the peak, oh, no, it didn't animate that here. Okay, kind of right in the peak period where the Ryles event tend to start, so around like 5,000–6,000 cubic kilometers of sea ice volume, and around 4.5 million million square kilometers of sea ice extent. So if the models are kind of capturing that correctly, we're kind of in the place where Ryle events wouldn't be unlikely to occur. Also, we've already seen increases in blocking events, really warm conditions in the wintertime in the Arctic, with corresponding drops in the sea ice. So sea ice was very, very low in the last winter. And so while statistically unlikely, it does seem like it's physically potentially possible to actually see something like that happen. So in summary, CMIP6 models show that the first ice-free day could be reached within 3 to 6 years from kind of where we're at right now. And so that means potentially before 2030, but it could also take much longer, 50 years, or if we keep warming between 1.5 and 2 degrees, we could also potentially avoid any ice-free conditions. The offset is around, is less than 6 years for most of the simulations, but it can be delayed. The first ice-free months can be delayed by up to 30 years. Such a rapid transition is very unlikely, but I think it's really important to not just predict the ensemble mean, but really look at the full range of what's possible so that we can really provide useful projections of what we might see in the Arctic over the next couple decades. And again, they are driven by extreme winter and fall and spring warms, driven by blocking events, warm air intrusions, and helped by storms that break up the ice. So thanks.
Thanks, Alexandra. Questions? Yes.
I have a question for a very interesting talk. So if you redo this using the 2012 as a target year to align the model with it, what do you expect to see? This is my first question. The second one is that if you're doing using the 1 year, but using a consecutive few years, like 2020 to 2023 as a benchmark to do similar thing, do you think that will be better constrain your future?
Sorry, the second question I didn't understand.
What? Like not only using 1 year, but using like a 3 year, 4 year.
Yeah, so we did do it for other years. We did like with.
I mean, just consecutive. Just like the just as the model not only capture the final year, but also the year preconditioning.
Yeah. Yeah, one of the interesting things is that not all, but I think at least half of the 9 quick transition simulations, where's my pointer, did actually have kind of something like we observe, kind of somewhat of a pause in sea ice loss. If we calculate the trend, often they're like positive or 0, just like we've observed. Yeah, we didn't look at whether. Yeah, we didn't make that criteria. For some of them, I think because I know at least for half of them we have that kind of pause. We would probably get the same, just fewer members that have that quick transition. If we looked at it from 2012, yeah, that's an interesting question because then we'd already kind of be halfway to that point, which kind of we know it didn't happen. And so that also means like if we start to see ice loss again, doesn't mean that we're going to quickly go to an ice-free Arctic. It's really something we'll have to see on a year-to-year basis. Like these drops that happen during Ryle events, as François was saying yesterday, they're bigger than what we've observed even in the early part of the century, but not by very much. And so kind of just a little bit more extended. If that had lasted for a little longer, or like the 2007, 2012 be a little closer together and get one more of those, we would have had kind of a Ryle event. So I hope that answered your question. Yeah.
I think we had a question from Camille and then François.
Thanks a lot for the talk. I thought you say at the beginning that you were doing some kind of model selection.
Yeah.
Can you explain a bit more based on what and like?
Yeah, so we looked at historical mean climate, mean sea ice extent, so that we took out the models that have a really high mean state and a really low mean state, because even though we kind of did that little adjustment, if they're too far off, then we would the forcing would be completely misaligned at that point. If we take a model that's still at like 8 million square kilometers in September, maybe it reaches 3.3 point at some point, but it'd probably be in 2090 or something, and so then the forcing would be very unaligned. And then the other part was we actually looked at the daily minimum and when that occurred, and for some models, but that was the less selective criteria. For some of them, it already occurred in late July, which seemed very unrealistic in terms of the seasonal cycle. And so since we were specifically looking at the seasonal minimum, we kind of didn't look at those models as well.
But all the selection is, I mean, you don't do any selection on the volume or something?
No, we didn't do any selection on the volume of the sea ice. We did look at the sea ice volume kind of to see if they're like very, very different. And they look similar to today. The spatial patterns are somewhat different, but like they're in the ballpark of kind of where we're at today. Yeah.
Okay. Thank you.
Thanks, François. Yes, yeah, let's one last question and then we'll...
Thanks a lot. And yeah, there have been previous studies showing that the phase of certain modes of variability can really define the time of ice-free conditions. And I was wondering whether you looked, for example, at the phase of the PDOs in these three realization that goes so quickly to ice-free conditions. And related to that, given that you have identified the meridional circulation and the blocking situation as a key predictor for ice-free conditions, could we actually assess, as of today, whether we are in favorable conditions to go to those ice-free conditions very soon? Because we have the data, right?
Yeah, yeah. I mean, it's a weather event, so like it's kind of, I don't know what would lead to kind of multiple years. So I think that's something that I don't think we really know, and I think there's also some just chance in it, because like this winter I was like, oh, we're seeing all these things that we just kind of saw in these model simulations, but we need multiple years of that in a row, and I think that's still the open question of like what really drives these routes, what leads to these perfect storms year after year after year for at least 4 years based on this definition, and so I think that's kind of still the open question of like what really leads to the conditions that kind of favor ice loss to occur for multiple years, because as we see, like none of them loses all the ice. I mean, once we get low enough, we could get to ice-free conditions, like because the variability is about 1.5 million square kilometers. So once we're kind of at 2.5 on average, then we could just get there in 1 year. But right now we're still far enough away that we need multiple years, and so we need something that kind of maintains these kind of modes. The other one, looking at the PDO, we didn't look at the PDO, but in a different project, we actually repeated like the screen and decile analysis and found that what was found based on the CSM is not reproducible in other large ensembles. Some don't seem to have any influence of the IPO on the first ice-free year, and ECERS, interestingly enough, actually has the opposite behavior to the CSM model, and so that's currently in revision, so I can talk to you more about that later. We didn't look at that in these cases, but it'd be interesting to kind of follow up on to kind of see if there's anything in these 9 extreme cases that would be interesting to look. Yeah. Okay.
Thank you. Thanks, Alexandra, again.